Welcome to this lecture on transition metal organometallic chemistry from principles to applications. Over the last few lectures, we have been discussing a very important topic, particularly about a important class of organometallic compounds. These are transition metal carbene complexes. Transition metal carbene complexes are important because they are important intermediates in many catalytic cycles. They serve as catalyst for many catalytic reactions, and that is why they become very important. Now, these transition metal carbene complexes are usually designated as 1 transition metal bonded to a carbenic moiety, which has a sigma bond as well as pi bond, and this carbon is having a sp2 center, sp2 hybridized carbon, which is multiply bonded with the transition metal. We have also seen that these transition metal complexes having this transition metal carbonic moiety have two kinds of interactions prevalent. One is ligand to metal, sigma interaction, and the other is transition metal to ligand pi interaction. Now, in our last class, we had seen that this kind of transition metal carbene complexes can be classified into two types. One is Fischer carbene, and the other is Schrock carbene. Now, each of these carbenes has a Cr2 moiety being bound to the transition metal, and each of these carbenes does show these two type of interaction. One is ligand to metal and the other is metal to ligand. Now, as for the Fischer carbene, we had looked into the reactivity, or we have looked into the bonding in terms of the molecular orbital responsible for this kind of Fischer carbene complexes. We have looked into the orbital interaction of Cr2 fragments with that of the orbitals of the transition metal, and what we saw that this is comprised of two interaction. One is ligand to metal sigma bonding interactions that involved metal d type orbital, which is empty, interacting with a ligand sp2 carbonic moiety. So, here this is filled and this is empty, and the ligand is donating electron onto the empty metal orbital, and this is represented by Tm ligand to metal sigma interaction. We had also seen that the second component of this transition metal to ligand pi interaction consists of metal d orbital interacting with an empty pz orbital of the ligand, and this time around this one is filled and this one is empty, and the electron donation happens from the metal to the pz orbital at the carbonic center. So, this is designated by Tm to ligand pi type interaction. Now, in our last discussion what we had seen that in this kind of interaction the carbene center is in singlet spin state. That is because that there is that sp2 hybridized carbon center is occupied by 2 electrons and the pz orbitals remains empty. So, Fischer carbene represents a singlet carbene, and then there are two kinds of donation happening, one from the carbene lone pair donating to vacant metal d orbital, and then a metal full filled metal d orbital donating to vacant pz orbital, and that comprises these two kind of bonding. Now, if we analyze this interaction bit more closely, what can be seen that because of the sigma donation that happens from the carbene lone pair onto the transition metal, and that because of the back donation is not as prominent as that of the sigma donation, there is a partial positive charge at the Fischer carbene. So, over here there is a partial positive charge at the Fischer carbene, and hence Fischer carbene reacts as an electrophile or undergoes nucleophilic attacks. So, Fischer carbenes are singlet carbenes, and because of del positive charge on carbenic carbon, Fischer carbene reacts as electrophile. This is a significant property of Fischer carbene, and that arises because of predominance of this ligand to transition metal sigma donation, which is not fully replenished by the transition metal to ligand pi back donation. As a result, there is this partial positive charge on the carbonic center, and which transform Fischer carbene to react as an electrophile. Now, let us take a look at how the scenario develops in case of the Strock carbene. In Strock carbene, similarly we have two interaction, one involves metal to ligand as well as the other involves ligand to the metal. Now, in this case, in case of Strock carbene, the carbene is in triplet state. That means that sp2 as well as the pz orbital each are occupied by one electron each, and they covalently interact with singly filled metal orbitals. So, in case of Strock carbene, the analogous orbital diagram can be is drawn over here. For example, metal orbital interacting with a carbon sp2 type orbital and each having one electron. So, this conveys this transition metal to ligand sigma interaction. Now, this is a pure covalent interaction, one electron being shared by each of the metal as well as the carbene sp2 hybridized orbital, and both are partially half filled or half filled. Both of the metal and the ligand orbitals are half filled. Now, as far as the transition metal to ligand pi interaction is observed, similar scenario exists where metal the metal d orbital interacts with pz of the carbene, where each of these are half filled. So, this also is a sp2 orbital and the metal as well as the ligand orbitals are half filled, and they undergo a covalent interaction of the type pi type. And unlike in Fischer carbene, which had been a dative interaction, over here we have two bonds being formed simple by a covalent interaction, transition metal ligand sigma bond as well as transition metal ligand pi bonds. As a result, because of this Schrock carbonic center being triplet in nature, and that one electron resides in the CsP2 orbital as well as one electron in the Pz orbital, and they interact with partially filled metal orbitals of appropriate symmetry, giving transition metal ligand sigma bond as well as transition metal ligand pi bond. Thus, as a result of these, as the electronegative carbon is more electronegative than the transition metal, the carbonic center has a del minus charge always, and hence the Schrock carbene reacts as a nucleophile. So, because of del minus charge on carbonic carbon, Schrock carbene reacts as nucleophile. So, here we see that interesting correlation emerges out, that as the carbonic carbons are more electronegative than the metal center, in this case because of pure covalent bond being formed, the sigma as well as pi type, the carbene center is del negative, the carbonic center is delta negative, and as a result Schrock carbene reacts as a nucleophile. So, here we see that even though that two different reactivity emerges because of the nature of bonding that takes place between the carbene moiety and the transition metal. And what is seen that in Fischer carbene, which is a singlet carbene, two coordinate bonds form, and these two coordinates bond are ligand to metal sigma coordinate bond as well as transition metal to ligand pi coordinate bond, and as the extent of pi coordinate bond is not as effective as that of ligand to metal sigma coordinate bond, there is a partial positive charge on the carbonic center of the Fischer carbene, resulting in the Fischer carbene behaving like an electrophile. On the other hand, for the Schrock carbene, which is in triplet state, the carbene sp2 orbital as well as the MTPZ orbital, they are partially filled, that each is occupied by one electron. As a result, this carbonic moiety interact with the partially filled metal orbitals, resulting in transition metal ligma sigma bond and as well as transition metal ligand pi bonds. And owing to the greater electronegativity of this carbon than that of the transition metal, the two bonds, two covalent bonds that are formed are polarized towards carbon, resulting in carbon being del minus or partially negative, and because of this del minus charge on the carbonic carbon, Schrock carbene reacts as an nucleophile. So, we see two different kind of reactivity emerging out, the type of bonding that is present between the carbonic moiety and the transition metal, and the commonality between this bonding is that this bonding has two components, each of them have two components, that is ligand to metal sigma donation as well as metal to ligand pi back donation as well, but they pan out differently to give different kind of reactivities as discussed here. We are going to now probe this differential reactivity of carbene moieties in bit more details, looking at examples of such differential reactivity. So, as a result, one can to understand the reactivity, one can look up or draw various resonance structures that are possible for carbene complexes, and some of these resonance forms are drawn here, and these resonant forms which can either represent a Schrock carbene or a Fischer carbene would explain the kind of reactivity the carbonic center would show. So, I am going to illustrate the various resonance forms that are prevalent for metal carbene moiety down below. For example, one can conceive as L minus C plus X R, or it can exist as L N M double bond X R. That can also be sort of exists as L N M plus C minus X R, and that can also exist as L N M minus X plus C R, and let us designate this as some structures as A, B, C and D. So, what one finds that the structure A and B sort of, or A predominantly represents Fischer type carbene, where carbene center is positively charged and acts as an electrophile. So, this representation is more of Fischer type. Similarly, one can say that the representation C is more of Schrock type, as the carbonic center is del negative, and that it can act as a nucleophile, reacts as nucleophile, and this structure D is a extension of a Fischer type compound, which follows from a Fischer type canonical structure. So, this also is a canonical form that represents the Fischer type, and this is a neutral. So, what one can see is that the different canonical structures that exist for metal carbene moiety can vary from the metal center being positively charged to metal center being negatively charged, and similarly the carbon center being positively charged to carbon center being negatively charged, and certain and each of these canonical structure in turn represents the type of reactivity associated with particular classes of carbenes. That is, for example, the canonical structure A and canonical structure D is more of a Fischer type, whereas canonical structure C represents more of a Schrock type, and the kind of reactivity these carbene complexes exhibit. So, these carbene complexes being important intermediates which are very unstable otherwise, and somehow have been stabilized by forming metal carbene bond, have been characterized by various spectroscopic methods, and of these the most powerful one obviously is the X-ray single crystal crystallography, where both the examples of Schrock and Fischer type carbenes have been structurally characterized, and we are going to look at some of the structures of these structurally characterized metal carbene complexes and see how their structure sort of represents the kind of carbene they are classified into. So, in the next few minutes we are going to look at some of the classical examples of Fischer and Schrock carbene complexes that have been structurally characterized. So, for example, this chromium pentacarbonyl complex C O E T N M E 2, and the structure it exhibits its chromium, so chromium is surrounded by 5 carbonyls and then is bound to a carbene with oxygen and corresponding ethyl group, and then nitrogen with 2 methyl group. Now, the metal carbene bonds, what we see is slightly different, that these all 5 carbonyl compounds are not equivalent, the 4 of them being equivalent and the 5th one being slightly different, and what we see is that these 4 of these has a bond distance of 188 picometer, whereas this one is slightly shorter of 185 picometer, whereas the metal carbene bond is however much longer at 213 picometer. So, this is a metal carbon bond, this also is a metal carbon bond, that this is more shorter. That means that carbonyl the carbonyl moiety is more pi acidic, that means that CO is more pi acidic, as a result that there is metal to ligand back donation, metal to CO pi back donation is more prominent as opposed to metal to carbene back donation. So, this has sort of more stronger double bond character, resulting in much shorter bond, whereas the electron density of the chromium is not back donated much onto carbon. As a result, we see a longer chromium carbon bond. Also, the angle at carbonic carbon is somewhat between 105, this is 105 degrees, 105 and whereas this is 128 and 126 degrees from here to here. So, what it shows that this sp2 carbon has been pushed back from 120 to somewhat 128 and 126 on both sides, and this OCN bond has been become smaller as a result of these two bond expanding from their 120 values, and this has contracted from 120 to 105. The carbene oxygen bond lengths and carbene nitrogen bond lengths are 135 and 133 picometer. So, this clearly demonstrates the structural characterization of Fischer carbene complexes, where chromium pentacarbonyl is bound to a carbene moiety that contain heteroatoms like O and the nitrogen adjacent to the carbonic center, and also what it can be seen from here that there is a competition between metal chromium carbonyl metal ligand bonding as well as chromium carbene metal ligand bonding, and what we saw is the pi back bonding from metal to carbonyl is much more stronger than that of the pi back bonding from chromium to carbene. As a result, the bond distance between carbon and chromium is much shorter, 185 picometer as compared to 213 picometer from chromium to carbene. As a result, this shows that carbon monoxide is a more acidic ligand than carbene. So, with that, let me conclude what we have discussed in today's lecture. We have looked into a very important topic in today's lecture, particularly looked at the differential reactivity of two classes of metal carbene complexes. These are mainly Fischer carbene and Strock carbene, and what we saw that these two classes of carbene complexes display nearly opposite reactivity in a sense that one reacts as a nucleophile and the other reacts as electrophile, and what we saw that their differential reactivity arises from the type of interactions they show while making the bond carbonic bond with the metal. Fischer carbene being singlet in nature undergoes two ligand to metal, metal to ligand interaction, but these are of coordinative bond type, coordination bond type, and as a result the carbonic center is positively charged and reacts as an electrophile, whereas in the Strock case the carbonic center is in triplet spin state, and as a result it does interact with the metal, forming two bond metal ligand sigma bond and metal ligand pi bond, but these interactions are more covalent in nature, where it engages itself with partially filled metal orbitals. As a result of greater electronegativity of carbonic carbon, the Strock carbenes are more electron rich and has a del minus delta negative character on it that makes it behave like or makes it reacts like an nucleophile. So, that is a very interesting observation that we had seen, that can be explained by the kind of bonding interaction that this carbene show with the transition metal. We have also looked in this lecture at structural characterization of various carbene complexes, particularly with respect to X-ray diffraction, and for this chromium pentacarbonyl carbene complex. With that, I conclude today's lecture, and we are going to be discussing more on these properties, reactivities of carbene complexes, their characterization techniques that have been used to prove these complexes in the next lecture. Till then, goodbye and thank you.